Hi, my name is Sanjay Khanna, and I'm working on Coursera um, course from Duke University for Machine Learning Foundations for Product Managers. I am on the course module 6 and working on the course project. This is where we have to build a model to predict the energy output of a combined cycle power plant. The data set for this is given. There are like four parameters over here that or four features over here that kind of give a sense of that define the energy output, net electrical energy output here. And that's what we're trying to predict that in, once the model is ready, if these features change, what will be the impact on the energy so that we can do the necessary arrangement in the energy plan. Now, like I said, the data set for that is given. There was also a recommendation for using the Google Auto ML. I tried it. Boy, it was hard. Look at the failures, number of times I had to retry to do this. And the reason was the default workspace and the default quotas that you get, those are not sufficient for the default auto ML job. So there are a variety of parameters you would have to change in the default auto ML regression job. And I couldn't get it right. And when you try to go and change the quotas for wherever the errors are displayed, sometimes you see that in the quota settings and you are able to change it. Other times there is no access in the quota settings to change that. And that kind of, I couldn't crack the combination of all the things over there to make it work. So I moved to Azure, where I was successfully able to run the job, and I was able to get the model there. Now let's quickly look at the model over here. This is the experiment that I ran, and it says the best model is it says the name of the best model, but the algorithm used was ElasticNet. And standard scalar wrapper is just a wrapper on top of it to pre-process the data to scale the numbers to be used by the model. And the normalized root mean square is 0.06. That means the error prediction is about 6.1% wide in any direction, which is quite good. If we look at the other parameters for other metrics that this model calculated, 92%, 92.8% of the variance is explained by the model, which is great. Absolute error, which is like how wide your errors can be, roughly 3.6 megahertz. But if you go for the root mean square error, which is going to also explain and account for the larger error modes, you are going to get about 4.5. So if you were to use this model for real prediction, then you would plan for deviation of 4.5 megawatts in your system rather than 3.6. And normalized root mean square error, which was the metrics I was allowed to, one of the metrics that I was allowed to, you know, tune my model for, like there were multiple metrics and, given I'm running multiple algorithms, it was picking up the best algorithm based on this number, and the model was tuned to get the best possible value for this. Basically, this means that at the scale of the values that we were working with, there is about 6.1% or 6.6, 6.0% of the error for this scale. If I look at the hyperparameters for this model, I did not understand these are the parameters for the data transformation, which is a standard scale wrapper. I don't quite understand those, but for the one which is applicable for the algorithm, this was alpha. This model, ElasticNet, allows both lasso and ridge regularization. And this alpha tells whether to use lasso. This L1 ratio tells whether to use completely lasso or completely ridge, or kind of a combination of those. If this number was completely one, it is 100% lasso. And alpha is how much of this regularization affects the tuning and impacts the overall outcome. So that's the hyperparameter for the model selected. If I go into model and child jobs, I used multiple model. One was Elastic Net. Actually, I can show here as well in the configuration settings. The primary metric used was normalized root mean squared, like I said, and the models that or the algorithms that were picked up was lasso Lars and Elastic Net. And then based on that, there were some wrappers on top of it to pre-process the data. I used the k-fold cross-validation over here. The number of cross-validations were 5, so that was the fold. As we move on and see the output of all these different algorithms run and different iterations run, you can see PCA with lasso Lars. You can see standard wrapper with Elastic Net, multiple iterations of that with the tuning of hyperparameters. For each one of these, the hyperparameters are different. That's where they were tuned and rerun. And then there was an ensemble run as well to combine both of those. But the best rating on the parameter we wanted is coming out to this 0.6065 on the standard scale Elastic Net. And that's the algorithm with these hyperparameters, which is going to work for us for our prediction based on the training that we did and the variations of the training that we did. This is there is a lot of information in outputs and logs that I pulled together, or I tried to go through, and also looked at a plot between the predicted values and the values given in the data set, and you can see the difference. It's a quite a well explained model. Like 92% of the variation is all explained by the model itself. So the model which is coming out to be is quite fair. I ran another model just for the sake of it, where I didn't select the algorithms myself and allowed it to select the algorithm by itself. And that's where the top model was the ensemble. And I kind of went through various different algorithms of all kinds. You can see random forest in there. You can see XGBoost regressors, and all these are different ways of doing calculations and algorithms. And then there are different preprocessors as well. And the best winning algorithm was the routing ensemble here, and this is what the normalized root mean squared error for that. 4.1, like 4.1% of error at the scale that we had the data for, compared to 6.1% of the error with the previous job that I showed, which was let me pick up the algorithm name, which is the Elastic Net. So that's all I wanted to show. Thank you very much.